Welcome to today's session. Till now, we have seen a brief introduction to operations research. What is operations research? Where do we use operations research? All this we have seen. In operation research, we have many classes of problems that are available. Out of that, linear programming is one of them, which is quite very important. So we will be learning about linear programming from today. A linear programming model seeks to optimize. When I say optimize, it can be either maximize or minimize. So a linear programming model seeks to optimize a linear function subject to a set of linear constraints. A linear model consists of three major components. One is decision variables, second one an objective function, and third one a set of constraints. In detail, let us see what is linear programming now. A mathematical programming problem is the one which seeks to maximize an objective function subject to constraints. This we know. In basic algebra, we have seen that we are supposed to maximize or minimize a particular problem based on a set of constraints. If both the objective functions and the constraints are linear, then such a mathematical programming problem will be called linear programming problem, LPP. So what do we mean by linear? Linear functions are functions in which each variable appears in a separate term raised to first power and is multiplied by a constant, which could be either 0 or any value other than 0. So what do we mean by this? Any linear function will be a function or an equation in terms of variables where the variables are of power 1. So no x square term, x cube term, or square or cube terms of the variables are not permitted. So we have all the variables in its power raised to 1. Similarly, the constraints are also linear in nature, and one more thing that we need to consider in terms of the constraints is they need not be equations all the time. They can be inequalities as well. That is, linear constraints are linear functions that are either less than equal to type or equal to type or greater than equal to type. Okay. So why are this linear programming problems being studied? The importance of linear programming is many real world problems lend themselves to linear programming modeling. That is, many real world problems can be modeled using linear programming or can be approximated by linear models. Some very successful applications of linear programming, uh, to name few, are manufacturing problems, marketing problems, finance or investment problems, or advertising problems, or agriculture problems. So many such problems we will be looking uh, as problems that we solve in the later chapters. So how does this linear programming problem look like? The general form of linear programming problem. So as I said, first and foremost thing is optimization. So when I say optimization, it is either maximize or minimize. Maximize or minimize what? Maximize or minimize certain decision variables. Which are the decision variables here? X1, X2, X3, so on up to Xn. N decision variables are there, these decision variables have to be, we are supposed to find out the value of the decision variables in such a way that this objective function that I have, the objective function or the basic objective behind solving the problem is represented as a function, a linear function. This linear function has to be either maximized or minimized based on the type of the problem. What do we mean by based on the type of the problem? So if at all the variables that I have considered are representing profit, so what do we plan about a profit? Profit has to be maximized. So under such problems, we consider maximization. If at all my variable is representing cost, none of us would be interested in maximizing the cost. We will be interested in reducing the cost so that in turn I will be getting more profit. So if the variable is representing cost or the time spent on doing a job or effort, then I go with minimization. If at all it is profit or any such physical entity which has to be maximized, then I consider maximization case. So what is objective function? This objective function is a linear function of all the decision variables, a linear function of all decision variables. So x1, x2, x3, these are all the decision variables. These are all linear in nature and it can have coefficients. It can have coefficients C1, C2, C3, so on up to Cn. So these ob linear function, these decision variables in terms of a linear function, I am denoting it as z. This z is called the objective function. So my aim of solving the problem is to either maximize or minimize this objective function. Is it simply maximizing or minimizing the objective function? No. When we are performing the maximization or minimization, I have a set of constraints that I need to satisfy. So these constraints will be written next. So when I am looking at the general form of linear programming problem, first I'll have max or min, then the objective function itself subject to certain number of constraints. These constraints are also linear functions which may be equations. If at all I have equal to, I call it equations. If it does not contain equal to, if it contains less than or equal to or greater than equal to, then I call it inequalities, right? These constraints, which are either equations or inequalities, will be written next. So my basic idea is to satisfy all the constraints and in turn maximize or minimize the objective function. There is one more special kind of constraint which is called non-negativity constraint. That is, all the decision variables x1, x2, x3, so on up to xn should be greater than equal to 0. Why should be greater than equal to 0? These are representing physical entities of the real world. That means to say, let me say, the number of items produced, or maybe the height of a person, or the weight of the commodity used. So all these physical entities cannot be negative if it does not carry any meaning if it is negative. Think of the number of items produced is minus 5. Does it carry any meaning? Can I produce minus 5 items? It is not possible. So obviously, I might not produce anything. Then the value will be 0. If at all I am producing, it must be positive. Therefore, I am writing it to be either greater than or equal to 0. So it must be either greater than or equal to 0. Therefore, I call it non-negativity constraint. Okay. So the general structure of linear programming problem, we will have a look again. It should have either maximize or minimize the objective function. Then I need to have a set of constraints which are all linear in nature, which would be either equations or inequalities, followed by a special kind of constraint called non-negativity constraint. Okay. Next, the assumptions of linear programming problem. I have already discussed all this. So two important things that I need to discuss is the additivity and the continuity assumption. When I say additivity, see here, have a look at the constraints. Each constraint is a sum of all the decision variables. All the decision variables are added together to form one constraint. But one constraint has no interaction with the other. That means to say, two constraints are not combined by either addition or subtraction or multiplication or anything. They are completely independent. That is what has been specified here. The additive assumption says there are no interaction between the decision variables when it comes to constraints. Then the continuity assumption says variables can take any value given in the feasible range. See, whenever I consider a variable, it needs to have a domain. So I am specifying the domain here. So domain of the variables is it can be either 0 or greater than 0. It can take any value between 0 and plus infinity. And when I say between 0 and plus infinity, it has to be something which is known with certainty. So obviously it cannot be infinity, it can be some numerically definable finite value lying somewhere between 0 and infinity. Clear? So this is what the assumption says. So when I say it can take any value from 0 to infinity, it is not only in terms of integers. It is not only 1, 2, 3, 4 or 5 so on. It can take fraction values as well. It can take, let me say the decision variable can have a value 1.5 or 3.2 or 4.8. Any values greater than or equal to 0 up to infinity are permitted. These are some of the assumptions of linear programming problems. So, when we talk about the problem structure, the next stage is stepping into the solution domain. So, what are we actually trying to solve in linear programming? We are trying to either maximize or minimize the objective, right? The maximization or minimization of some quantity is the objective in a linear programming problem. So the aim or the objective of linear programming is to either maximize or minimize a certain quantity. So whenever I consider a problem, it can have any number of solutions. There is no compulsion that it has to have a single solution every time. So any solution which satisfies the constraints is called a feasible solution. A feasible solution satisfies the problem's constraints. Any solution which satisfies the constraints, what do I call it? Feasible solution. So out of multiple solutions, see, let me say, if at all I consider an example, how many of the students have cleared third semester? So there is no compulsion that there has to be only one student who has cleared. Anybody who satisfies the constraint of scoring 35% of marks is considered to be cleared. They are all feasible solutions. All the students who have scored more than 35% are feasible solutions. But when I say who has secured the highest marks, then there is only one out of all these feasible solutions which turn out to be the final answer. That final answer is your optimal solution. An optimal solution is a feasible solution that results in the largest possible objective function value. So when I'm talking about maximization case, when I asked you who has got the highest marks, then the optimal solution is the largest possible value in all the feasible solutions. Out of all the people who have cleared, whoever has got the highest marks, that will be the optimal solution. If at all I ask you who is the least scorer in the class, then the smallest possible objective function value will become my optimal solution. The final answer will be the smallest possible value. Okay, so this is a brief look into the solution domain. So this linear programming problems can be solved using graphical method, simplex method, and multiple methods are there. But out of which I will be telling you only about graphical solution today because it has an additional constraint or a limitation on it. See, graphical solution or graphical method can be applied on linear programming problems with only two variables. If at all I have two decision variables, then I can apply graphical method. If at all I have more than two variables, graphical method cannot be applied. What is the reason? The reason is quite very simple. If at all I am supposed to solve it using graphical method, I need to make use of a graph sheet. If at all I need to make use of a graph sheet, how many axes do I have in a graph sheet? I have an x-axis and I have a y-axis. I have only two axes available. So the third axis is not supported. So obviously I cannot support a third variable. So that means to say, if at all I have only two decision variables in the linear programming problem, then I can apply graphical solution method. If not, graphical solution method cannot be applied. Fine. This is a brief look into the solution domain of linear programming problem. So next, in our next class, we will be looking at how to frame linear programming problems. That is, from a real world scenario. Let me say, in form of a paragraph, they have given you a real life situation. So that means to say, okay, there is a particular product A available with you. There is a product B which is available with you. The amount of product A that you have is 8 kgs. The amount of product B that you have is 10 kgs. And you are interested in manufacturing finished goods called G1 and G2. So to manufacture G1, you require 2 units of A and 3 units of B. And to manufacture G2, you require 2 units of A and 2 units of B. So if this type of a real world scenario is given, how do we write it in form of a mathematical problem or in terms of a linear programming problem? That is trying to fit in a real world scenario into the framework of linear programming. This is called formulation of linear programming problems that we will be looking at in our next class. Till then, thank you for listening to the lecture. very patiently. To briefly recap what we have done today, we saw what is linear programming problem. Uh, we defined what is linear programming. Then we saw the structure of linear programming or the general form of linear programming problem. Then we looked into the constraints or the assumptions that we have for linear programming problems. Then we had just had a brief look at the solution domain of linear programming. So thank you. Kindly stay home and stay safe. Uh, this is quite very important as it is the lockdown period. Kindly stay back home and stay safe. Thank you.